Okie dokie, we're going live. And tonight we're going live on Twitch, Twitter as well, X, whatever you want to call it. So I'm just going to check both of those are working as expected. Is my sound? Yep, sounds there. Okay. Okie dokie, we're going live. Right, that's all fine. Right, let's see if we can get Twitter going. Don't exactly know how this works with Twitter. How do I tell if I'm live on X? I'm not really sure. Oh, let me go to the Is it just because it's not the time yet, or 31st, 8 p.m. No, it's not 8 p.m. yet, but got that set, so okay. Guess we'll just kill time for a minute. I get that going. Oh, I might be live now. Feel me? I might be live now. Feel me? Yeah, I got it. Okie dokies. Okay. Right, I think that's YouTube and Twitter set up now, doing good. So should be fine to just leave those, and we can get cracking with this. So, yep. So welcome back, everyone. This is the series at the minute where I am going through learning Go. So, watched a whole bunch of tutorials last time. Spent a lot of time going through semantics, learning all the basics and stuff. I mean, saying basics. We're going to learn the basics now because we'll get tucked in. But yeah, so we went through some nice tutorials last time. I was really grateful for those who put those up there. And the idea of tonight is we're going to go through a tour of Go. Now, I don't know how long this is. I don't know how, I know there's quite a few sections and stuff, but we're just going to start from the beginning. So this is the welcome page. This is like the very, very first page on everything. And I'm just going to crack on. So I'm going to go through things. I'll read stuff out. If my head's in the way a little bit, I can't really help that. But yeah, off we go. So, and I'll read it through so like people don't have to read their own thing and stuff. They can keep it where I'm up to and stuff as well. So let's get to it. So, hello, welcome to a tour of the Go Welcome to a tour of the Go programming language. The tour is divided into a list of modules you can access by clicking on a tour of Go at the top of the left of the page. You can also view table of contents at any time by clicking the menu on the top right. Yeah, I can see that there. That's useful. Cool. You can also view the table of contents at any time by clicking on the menu. Oh, I already said that. Throughout the tour, you'll find a series of slides and exercises for you to complete. You can navigate through them using previous, page up, or previous or page up to go to the previous page, or page down to go to the next page. The tour is interactive. Click Run button down below, or press Shift and Enter. Probably just Shift and Enter. Does that work if I'm anywhere, or do I have to be in the... Right, only if I'm there. Okay. All right. If I tab around, I can't really tab around. Right. It's page up, page down. Okay. Right. Okay. I don't want to go next. Right. Yeah. Okay. Tor is interactive. Click run now. Run button now to compile and run the program on a remote server. The result is displayed below the code. These example programs demonstrate different aspects of Go. The programs in the Tor are meant to be starting points for your own experimentation. Edit the program and run it again. So if I run it just once, it's going to print hello. Yep. That works quite nicely. Cool. When you click Format, Control and Enter, the text in the editor is formatted using the Go FMT tool. You can switch syntax highlighting on and off by clicking the syntax button. When you're ready to move on, click the right arrow or the page down. So I've got page down button on my keyboard, so I'll do that. Yeah, I might have to think of another window setup because like you guys can't see any of this and stuff. So it says the Tor is available in other languages, Brazilian, Portuguese, yeah, all those languages. Really, really cool. Got the literature. I wonder how that actually works across programming languages for different typing. So click the next button on page down. Go offline optional. So this Tor is also available as a standalone program that you can use without access to the internet. It builds and runs the code samples on your own machine. To run the Tor locally, you first need to install Go, then run this. This will place a Tor binary in your Go past bin directory. When you run the Tor program, it'll open a web browser displaying your local version of the Tor. Of course, you can continue to take the Tor through the website. I'm just going to stick through the website for this. Okay. So this Tor is built atop the Go Playground, a web service that runs Golang orgs servers. The service receives a Go program, compiles links, and runs the program inside a sandbox, then returns the output. There are limitations to the programs that can run in the playground. In the playground, the time begins at the 11th of November or 11th of October or the 10th of November 2009. 11 o'clock at night. Determining the significance of this date is in an exercise for the reader. This makes it easy to cache programs by giving them deterministic output. Okay. There are also limits on execution time and on the CPU and memory usage, and the program cannot be accessed external network hosts. The Playground uses the latest stable release of Go. Read inside the Go Playground to learn more. So welcome Playground. Time is time.now. Okay. We don't need to read about that right now. So yeah, congrats, you finished the first module of the Tor. Now click a tour of Go to find out what else you can learn about Go, or go directly to the next lesson. Do page down, let go. Does that go to the next lesson? Yes, it does. Cool. Packages. Every Go program is made up of packages. Programs start running in package main. This program is using the packages with imports fmt math/rand. By convention, the package name is the same as the last element of the import path. For instance, math/rand package comprises files that begin with the statement package rand. Okay. So this is a thing of some functions. So my favorite number is 8. For it again, my favorite number is 4. Cool. Imports. This code groups the imports into parenthesized factored import statement. You can also write multiple import statements like import fmt, import math, or you can do it in this sort of array-based format. That's good. But it is good style to use the factored import instead. Okay, it's called factored import. Okay. In Go, a name is exported if it begins with capital letter. For example, pizza is an exported name, as is pie, which is exported from the math package. Okay. Pizza and pie do not start with capital letter. Go. A name is exploited if it begins. Right, okay. Right, so you don't have an export keyword, it's just done. Pizza and pie do not start with capital letters, so they are not exported. When importing a package, you can refer only to its exported names. Any unexported names are not accessible from outside the package. Run the code, notice the error message. To fix error, rename math.py to math.py. Okay, run it. Okay. Ta-da! Easy peasy. A function can take 0 or more arguments. In this example, add takes 2 parameters of type int. Notice that the type comes after the variable name. For more about types, why types look the way they do, see the article on Go's declaration syntax. Okay, so there's no like colon separation, it's just by space. Okay, so takes an int, print that out, 55. Simple, okay. Functions continued. When two or more consecutive name function parameters share a type, you can omit the type from all but the last. In this example, we shortened xint, yint to xyint. Okay. And they're all the same. And the return of that is int as well. Guess what? That's what that means. Function, yep. It's simple. Simple at minute. Multiple results. A function can return any number of results. The swap function returns 2 strings. Okay. So that's like that's a different way of assigning variable. Can't remember what the name of that is. And then you get 2 variables back. Both strings. Both the same. Hello world, yep. Oh, world hello, yes, what we're in. Okay. Name return values. Go's return values may be named. If so, they are treated as variables defined at the top of the function. Go's return values may be named. If so, they are treated as variables defined at the top of the function. These names should be used to document the meaning of the return values. A return statement without arguments returns the named return values. This is known as a naked return. Okay. Naked return statements should be used only in short functions. As with the example shown here, they can harm readability in longer functions. Yeah, I imagine, because you're sort of making an assumption that somebody's going to be able to see, like, or trace it back up to the top. So it'll return x and y. X will be sum, so it'll be 17 times 4 divided by 9, so 17 times by 4, oh no, mental arithmetic. 34, 68. 68 divided by 9. How many 9s go 68? Give me a minute. 49. Oh, 45. 45. 54. 65. And y, so it'll be 65 and then sum take 17 take. I can't hold that in my head. All right. What did I work out wrong there? Must have done FODMAT wrong. Okay, move on. Variables. The var statement declares a list of variables as in variables. The var statement declares a list of variables as in function argument lists. Type is last. A var statement can be at package or function level. We see both in this example. Yeah. So these are all booleans, yeah. And then there's another one instantiated here, declared here. So I. So that'll just be, I'm not sure actually. What would that be by default, like 0? 0, false and false and false? Yeah, okay. Right. Variables and initializers. A var declaration can include initializers one per variable. If initializer is present, the type can be omitted. The variable will take the type of the initializer. Var declaration can include initializers, one per variable. Okay. If initializer is present, the type can be omitted. The variable will take the type of the initializer. Okay, right, so that's going to be like that. So I is going to be, yeah, 1 and 2. True, false, and no. I put it's going to give me a problem, isn't it? Yeah, can't we use untyped constant like that? If I did that, it's still going to be the same numbers, isn't it? Stuff. Okay. Short variable declarations. Inside a function, the colon equals short assignment statement can be used in place of a var declaration with implicit type. Okay. Outside a function, every statement begins with a keyword, var, func, and so on. And so the short assignment construct is not available. It's only inside functions. Okay. And that auto assigns the type, so that will assign that to 3. So if I put a string, it's going to throw up on that. But if I change it to a... Oh. Then I'd be fine with it. Nope. I'm expecting to name it string at the end of a statement. To be double. It can't be string if it's... Right, so you can't give it a type if it's this shorthand. No, you can't. Okay. But you can with the var keyword. Okay, makes sense. Basic types. Go's basic types are bool, string, int 8, int 16, int 32, int 64. uint 8, and then I'll to that 64, and then uint ptr. Byte. That's an alias for uint 8. Rune, alias for int 32. Okay. Represents a Unicode point. Okay. Float 32 and float 64, complex 64 and complex 128. The example below shows variables of several types, and also that variable declarations can be factored into blocks, as with import statements. The example shows variables of several types, and also that variable declarations may be factored into blocks, as with import statements. Okay. Right, so it can be turned like that. That's a variable name type, and that. Square root, I'm guessing. The heck is that? I. Where's I come from there? Okay. The int, uint, and uint ptr types are usually 32 bits wide on 32-bit systems and 64 bits wide on 64-bit systems. When you need an integer value, you should use int, unless you have a specific reason to use a size or unsigned integer type. Okay. I'm guessing these like print lines, so these become like placeholders. That comes after. But that's something particular because that's the type. So that must actually, so the %t must be a type, and then the %v must be value for those two. Okay. All right. Zero values. Variables declared without explicit initial value are given their zero value. The zero value is 0 for numeric types, false for the Boolean type, and empty string for strings. Makes sense? Don't think a lot of other programmed languages do it different. So that's value in Q. I wonder what that is. So for the string, I don't know. I'm not sure what that means. We'll figure that out at some other point. Must mean like the, I don't know, just the full value, like including like the what you call it, the quotes. I'm not sure what it actually means with the Q. We'll figure that out later. Type conversions. The expression t brackets v converts the value v to the type t. Some numeric conversions. The expression of tv converts the value v to type t. Right, okay, it's a placeholder, right, so you can change. So some numeric conversions, so I is an int of 42, f is a float 64, so float 64, and plug I into that, and I'll change that. U and then uint with f around it, I'll change the float 64 to a uint. Or put more simply, without the var statement, so the short assignment. I is equal to 42, f, so it inherently takes the type. Yeah. Unlike C, in Go, assignment between items of different types requires an explicit conversion. Try removing the float 64 or uint conversions in the example and see what happens. Can I use as float value an argument master square root? Can I use f in variable type float 64? Okay. Yep. Cool, makes sense. No whoopsies back since then. Hold on, forgot to put timer. Right, timer's on. Okay, so type inference. When declaring a variable without specifying an explicit type, either by using colon equals syntax or var equals expression syntax, the variable's type is inferred from the value on the right-hand side. On the right-hand side, the declaration is typed. The new variable is of the same type. On the right-hand side, the declaration is typed. The new variable is of the same type. But when the right-hand side contains an untyped numeric constant, the new variable may be an int, float 64, or complex 128, depending on the precision of the constant. So try changing the initial value v in the example and observe how the type is affected. If I just change that to 128, the type of int, what was it previously? 42. Still an int. If I change it to over 9,000. Still type of int. So if I change it to 3.142, changes to inherently a float 64. And then 0.8667 plus 0.5i. Alright, I must be a special character then. V is of a type complex 128. Okay. Okay. Constants. Constants are variables, but with the const keyword. Constants can be character, string, boolean, or numeric values. Constants cannot be declared using the : syntax. Okay, so constants pi is 3.14. So world hello, print hello, and then word in Chinese, Cantonese, not sure. Then happy pi day, so happy 3.14 day. Const truth equals true. Go rules, true. Numeric constants. Numeric constants are high precision values. An untyped constant takes the type needed by its context. Try printing need int big 2. An int can store the maximum a 64-bit integer, and sometimes less. Right, I'll read that again. Wasn't concentrating very well. Numeric constants are high precision values. An untyped constant takes the type needed by its context. Try printing need int big 2. An int can store maximum 64-bit integer and sometimes less. So create a huge number by shifting 1 bit left 100 places. In other words, the binary number that's following the 1 by 100 zeros. Shift it right again 99 places, so we end up with 1 is less than 1 or 2. Create a huge number by shifting a 1 bit left 100 places. In other words, the binary number that is followed by 100 zeros. Shift it right again 9 places, so we end up with 1 or 2. Big. Not too sure what that comparison means actually. What does that mean? So go. What does that mean? The super possibly oversimplified definition is that is used for times 2 and is for divided by 2. And the number after that is how many times. So n times by 2, n times by 2, x times n. Y divided by 2 is z times. For example, okay. So that would be 1 divided by 2, so 0.5, times by 100 times, so 0.5 times by 100. $50. Probably getting that wrong. Numeric constants are high precision values. An untyped constant takes the type. Try printing need int big 2. Can it use big untyped int? Can it use big untyped int constant as int value in argument to need int overflows? Fade. Okay. Don't think I quite understood what was going on there, so if the maths was a little bit heavy for me and stuff, but if you finish this lesson, you can go back to the list of modules to find what to learn next, or continue to the next lesson. On we go. In fact, hold on, what are we up to in this? Alright, yeah, we're going to have plenty to do, so we've got flow control. It's not really obvious like where the indent is, so can't really tell. Is this the... Oh right, okay, this is the opening of the whole thing, so like there. So then it'd be more types, methods, and okay, I've got plenty to crack on with. Didn't expect this to be short anyway. Okay, so for Go has only one looping construct, the for loop. The basic for loop has 3 components separated by semicolons. The init statement executes before the first iteration. That's that. So that's that part. The condition expression evaluated before every iteration, so this part. And the post statement. Execute at the end of every iteration. Same as most. The in statement will often be a short variable declaration, and the variables declared there are visible only to the scope of the for statement. Makes sense? The loop will stop iterating once the Boolean condition evaluates to false. Yep, same as always. Unlike other languages like C, Java, or JavaScript, there are no parentheses surrounding the 3 components of the for statement, and the braces are always required. Simples. Yep. So that's a sum of everything from 1 to 9. Okay. Well continued. The init and post statements are optional. Cool. Easy. For is goes while. At that point, you can drop the semicolons. C's while is spelled for in Go. Okay, so you can just get rid of everything altogether. So yeah, you don't need the semicolons after that. Nice and elegant. If you omit the loop condition, it loops forever. So an infinite loop is compactly expressed. What's that going to do if I execute that? I guess I'm going to put a timer on it, but yeah. Go's if statements are like its for loops. The expression need not be surrounded by parentheses, but the braces are required. So if you want to be neat, you can put them in parentheses, but otherwise not. So it's a square root function. If x is less than 0, then return the square root of minus x plus I. makes it into a string, I imagine. So format, sprint, not sure what that does. Math square root of x. Alright, so return at that point. Okay. So it's going to pass in 2 to the square root and minus 4. Okay. If with a short statement. Like for, the if statement can start with a short statement to execute before the condition. Variables declared by the statement are only in the scope until the end of the if. Try using v in the last return statement. If with a short statement. Like for, the if statement can start with a short statement to execute before the condition. Alright, okay. That's interesting. A little bit, I'm not sure if I'd use that, but variables declared by the if statement are only in scope until the end of the if. Try using v in the last return statement. So it's not going to be there, is it? Yeah. Obviously. Nope, not there. Makes sense. If and else. Variables declared inside an if short statement are also available inside any of the else blocks. Both calls to POW return the results before the call to fmt println in main begins. Okay. Also available inside any of the else blocks. Turn those up before the call to fm println in main begins. Yep, okay, easy there. Yep, cool. Exercise, loops and functions. As a way to play with functions and loops, let's implement a square root function. Given a number x, we want to find the number z, for which z squared is most nearly x. Computers typically compute the square root by using x using a loop. Starting with some guess z, we can adjust based on how close z squared is to x, producing a better guess at that. I don't know. I'm not going to pretend to understand that. Repeating this adjustment makes the guess better and better until we reach an answer that is as close to the actual square root as can be. Implement this in the func square root provided. Yes, it's empty in a minute. A decent starting guess for z is 1, no matter what the input. To begin with, repeat the calculation 10 times and print each z along the way. See how close you can get to the answer for various values of x, 1, 2, 3, and how quickly the guess improves. Hint: to declare the initialize a floating point value, give it floating point syntax or use a conversion. Next, change the loop condition to stop once the value has stopped changing, or only changes by a very small amount. See if that's more or fewer than 10 iterations. Try other initial guesses for z like x or x divided by 2. How close are your function results to math square root in the standard library? Now, if you're interested in the details of the algorithm, z squared minus x above is how far away z squared is from where it needs to be x in the division. By 2z is the derivative of z squared. To scale how much we adjust z by how quickly z squared is changing. The general approach is called Newton's method. It works well for many functions, but especially well for square root. Okay. So if we're at the minute, what's it going to do? Nothing. No return statement. So, what was it saying about this? Computer starting with some guess, we're just based on how close z is to the... Repeating this adjustment makes the guess better until we reach an answer that's close to the actual square roots can be. Implement the func square root provided. Decent starting guess for z is 1, no matter what the input. To begin with, repeat the calculation 10 times and print each z along the way. See how close you get to the answer for various values of 1, 2, 3, and how quickly a guess improves. To declare and initialize a floating point value, give it floating point syntax or use a conversion. I guess part of the thing is if you return, and it was saying whatever's like declared like this, the thing that's going to be returned last, so 1.0. Then it mentioned this formula. So if we run that, not enough value return values have not enough return values have one float. Square root of 2 is 1 point. One point one, 1.4, blah 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 blah. So we want this to loop really, don't we? So hold on. So we're saying 4. Oh, I forgot the syntax already. Forgot the syntax for the loop. Hold on. It was you needed like equals 0, and then it was a thing that it didn't need a what you call it. So I equals 0, and then semicolons. So then it was I is less than 10, and then I plus this. Yeah, why should you do that? Okay. God, they get some really mathsy things in here. Like, I didn't realize I was going to go this hard. But we work. Okay, so switch. A switch statement is a shorter way to write a sequence of if-else statements. It runs the first case whose value is equal to the condition expression. Go switch is like the one in C, C++, Java, JavaScript, and PHP, except that Go only runs the selected case, not all cases that follow. In effect, the break statement that is needed at the end of each case in those languages is provided automatically in Go. Another important difference is that Go switch cases need not be constants, and the values involved need not be integers. Okay, so switch. So we defined OS is equal to runtime.goose, wherever that is. I'm not sure what that is. OS, so switching on OS, it's Darwin. It prints OS X, Linux, prints Linux, default, BSB, blah, blah, blah. Windows prints the, not sure what that is. See what it is? Go runs on Linux. Okay. Switch evaluation order. Switch cases evaluate cases from top to bottom, stopping when a case succeeds. For example, case 0, case f on a function does not call f if I is equal to 0. Note, time in the Go playground appears to start in 2009 UTC, a value whose significance is left as an exercise for the reader. Is that when the language was created? I'm not sure. I guess that one yet. So when's Saturday? Today is time now, weekday. Well, what day is it? Thursday, right? Yep, Thursday. So switch time Saturday. Not sure what that gives back. And today plus 0. Weekday, so that'll give the number. So I guess I'll give number 4. So today plus 2. Saturday, I'm guessing, will be 6. So it'll be today plus 2, so it'll be that one in 2 days. Depending on where the server is. Too far away. What is today on here? Tuesday. Oh, right. Oh, it was saying, yeah, it's always going to be the same day. It's not the day today, is it? So it's always Tuesday. Okie doke. Switch with no condition. Switch without condition is the same as switch true. This construct can be a clean way to write long if then else chains. Switch without condition is the same as... Oh, right. Okay, I see. Right. Okay. Yeah, because you don't have the if else thing going on. You can just do switch like that. I'm not sure I like that, to be honest, but it's okay. Not really too keen on that syntax, but defer. A defer statement A defer statement defers the execution of a function until the surrounding function returns. Defer statement defers the execution of a function until the surrounding function returns. Right. The deferred call's arguments are evaluated immediately, but the function call is not executed until the surrounding function returns. Okay, so it's going to say hello, then world. Okay, so it's executed this part, but it doesn't run. It's evaluated, but it's not executed. So this runs first, and then the whole block, the whole scope is done, and then it runs that. So I put fmt dot. Whoops. Howdy, hello world. Okay. Stacking defers. Deferred function calls are pushed onto a stack. When a function returns, its deferred calls are executed in last in, first out order. Deferred functions calls are pushed onto a stack. When a function returns, its deferred calls are executed in last in, first out order. To learn more about deferred statements, read this. So last in, first out. Right, okay. So it's stacking like this, stacking up like that, but then it goes top down again. Okay. So then it'll be counting. It starts at 0, it goes up to 9, but it'll be done 10 times. No, it'll start with 0, so it'll be counting, and it'll be 9, 8, 7, all the way to 0, like that. Yep. Cool, that's what I expected. Just checking my logic. Bingo. You finish this lesson, you can go back to the list of modules to find out what's next or continue to learn with their next lesson. Next lesson we go. Right, what's on? Yeah. Oh, some people watching on Twitter. So, some people on Twitter, how you doing? I've not really got a great setup yet to be able to sort of have a like a live chat like kind of going, like keeping tabs on all chats and stuff. So something for the future. I'm gonna try and get a only got one screen to like work off. So I'm gonna have to get like a little sort of like mini screen I'm gonna put underneath. You can't see me while I'm waving my hands over here. To go under my screen. Probably put the chats up in there. But another time. Cool. So pointers. Go has pointers. A pointer holds the memory address of a value. The type asterisk t is a pointer to a t value. So type. So like in right. Yeah. Its 0 value is nil. No address, right? And the AND operator generates a pointer to its operand. Okay. The asterisk operator denotes the pointer's underlying value. Sorry, you can't read this under my headspace, but like, there we go. The asterisk operator denotes the pointer's underlying value. So, sorry, I know it's going to be hard to switch the screen. There you go, so you can read it. The operator denotes the pointer's underlying value. So read I through the pointer P. So P generates a pointer to its operand, so it points to the value of that. Okay. type t p int. So pointing to a t value. So an int value. So p is an int value. Right, okay, we call it that, and then we assign that to. So that'll be int. That int's int as well. If it wasn't, it would freak out. As well. Operator. This is known as dereferencing or indirecting. Unlike C, Go has no pointer arithmetic. Okay. So, pointer I, so pointer value I, so 42, and print read I through the pointer, and then that type is a pointer to the value to a t value. So set I through the pointer, so that will set I to 21. And you print I, you see the new value. So that'll be 42, 21. I'll finish this off actually. So point to J, 42. 2701, 2701. Divide J through the pointer. So through the pointer. So 2701 divided by 37. I'm going to try and pretend and figure out what that is. See the new value. So it's not going to be 2107. It's going to be whatever it calculates out to be. Yep. So 42, 21, like I said, and then 73. Right. That makes sense. Thank you, the Cloud Deck on YouTube. Some nice gospel references there. Thank you very much. Hope you're doing well. Don't left anything on Twitter. Can't really tell the Twitter. I don't know how it works. Imagine something's happening, but not sure what. Okay, right, that makes sense. So, and is to point. So no. And operator generates the pointer. Yeah. Okay, so that generates the pointer. So that generates a point for that. So that just basically says point to this. This says what do they call it again? Pointer. So that's a pointer. Operator generates a pointer, so that reads the pointer, that sets the pointer. Asterisk operator denotes the pointer's underlying value. Okay. A struct is a collection of fields. So not quite like an object, I imagine, but similar. So vertex 1 and 2. Okay. Just prints that. Okay. Be interesting to see how they're different to objects. Struct fields are accessed using a dot. So you create the vertex, then v dot. Yep. That's simple enough. Pointers to structs. Struct fields can be accessed through a struct pointer. Struct fields can be accessed through a struct pointer. To access the field x of a struct, when we have the struct pointer p, we could write asterisk p.x. However, that notation is cumbersome. So the language permits us instead to just write p.x without explicit dereference. That creates the pointer for v, and then p can just do that. But you would have to, okay, pointers to structs. So structs have some sort of fanciness. I hope you learn along with me as well, guys, because I'm just a complete noob to this. I got no idea, totally new to go. Enjoying it so far, and we'll be picking up. We'll kind of go through enough sort of hands-on tutorials and stuff. Going to be picking either some tests, challenges, or like some simple projects to start building things. And yeah, follow along for the journey. Thanks for being here. Struct literals. A struct literal denotes a newly allocated struct value by listing the values of its fields. Literal denotes a newly allocated struct value by listing the value of its fields. You can list just a subset of fields. Oh, excuse me. You can list just a subset of fields by using the name syntax, and the order of named fields is relevant. Struct literal denotes a newly allocated struct value by listing the value of its fields. You can list just a subset of fields by using the name syntax. Right, okay. Name colon syntax, right. Okay. The special prefix and returns a pointer to the struct value. So this is going to be 1, 2, oops, I already ran it and stuff, but 1, 2. And then vertex x is going to be 1. Y is going to be 0. It's going to be 0 and 0 because there's nothing given. This is struct literal, okay. P, and then it's going to point to the vertex of pointer has it 1, 2. So P there. Oh, let's get that back on. It's going to point to and vertex 1, 2. It's just going to be the same and 1, 2, pointer 1, 2. Okay. Right. So makes sense. Arrays. The type T is an array of n values of type T. The expression var a 10 ints, so like it's an array of ints starting with 10. Declares a variable a as an array of 10 integers. 10 integers. Oh, right, I see. Right, it's not the entry, it's not the value of the thing inside. Oh, right, okay. An array's length is part of its type, so arrays cannot be resized. This seems limiting, but don't worry, Go provides a convenient way of working with arrays. Right, so that's saying it's got like two strings in that array. The first one's going to be hello, the second one's going to be world. Zero-based arrays again. So hello world, and then I'm not sure what that prints, so I'll print the same, pretty much. Don't know how it deals with arrays in a print. Primes, so it's going to be 6 numbers long, and the 6 numbers are going to be 2, 3, 5, 6, 7, 11, 13. So that'll just print out that, I imagine. Hello world. Yep, so hello world with the bracket around it. Okay. Slices. An array has a fixed size. A slice, on the other hand, is a dynamically sized, flexible view into the elements of an array. In practice, slices are much more common than arrays. Arrays has a fixed size. A slice in the hand is dynamically sized, flexible view into the elements of an array. In practice, slices are much more common than arrays. The type brackets t, square brackets t, it's a slice with elements of type t. Okay, so it's more like what we're sort of familiar with. A slice is formed by specifying two indices, a low and a high bound separated by a colon. So A, low, high. This selects a half open range, which includes the first element but excludes the last one. The following expression creates a slice which includes elements 1 through 3 of A. Okay, so primes, so 6 integers long, 2, 3, 5, 7, 11, and 13. And the slice is going to be, var s is going to be an array of integers. It's going to take primes and it's going to take slice 1 to 4. So it's going to be, when it prints out, it's going to be 3, 5, 7, and 11. 3, 5. How's that work? Right, okay. Right. That's not that, is it? It's a low and a high bound. Oh, it's not inclusive, right? Right, that's what it's saying on that line. So which includes the first element, excludes the last element. Right, okay, so you could just think of it as 1 and... Oh, no, I guess that makes sense. Right, a little bit confusing, but slices are like references to arrays. Slice does not store any data; it just describes a section of an underlying array. Changing the elements of a slice modifies the corresponding elements of its underlying array. Array data, it just describes a section of an underlying array. Right, okay. Other slices that share the same underlying array will see those changes. That's interesting. So changes to 1 changes them all. So we've got names, we've got John, Paul, George, Ringo. Wonder who they are. Never heard of them before. The apostles? No. So that'll print out all the names with the brackets around, square brackets around John, Paul, George, and Ringo. And A will be John and George. John and George. And then B will be Paul and Ringo. So it would be John, George, Paul, and Ringo. And then they're changing B0 to... So that'll be John to XXX. Anyway. And then we'll print A and B again. So it'll be XXX, George, Paul, and Ringo. And then all printed out together will be X, Paul, John, and Ringo. Yeah, okay. That's cool. That's interesting, that. So they're mutable. Slice literals. A slice literal is like an array literal without the length. This is an array literal. A slice literal is like an array literal without the length. It's an array literal. Yep, so 3 3 items in an array, but all booleans true, true, false. And this, excuse me, and this creates the same. This creates the same array as above, then builds a slice that references it. True, true, false. Okay, so that's Q. It's got 2, 3, 5, 7, 11, 13, all prime numbers. It's a slice. So we print that, prints out the whole lot. Then R is equal to true, false, true, false, true, false, true, true, false, true. So that's going to be a slice as well. We print all out, it's going to be all that. There's a struct of fields. So it's be an array of structs. S is going to be an array of structs. So then it's going to be, int and boolean. So I and B. So I, B, okay. Yeah. Okay. That's interesting. Slice defaults. Hi, Elliot Gill. How's it going? On YouTube. Love your video. Thank you. Which one? This one? I'm just learning at the minute. Hope you're doing well. Hope you're learning along. What we're doing. So, slice defaults. When slicing, you may omit the high or low bounds to use their defaults instead. When slicing, you may omit the high or low bounds to use their defaults instead. The default is 0 for the low bound and the length of the slice for the high bound for the array. So var a 10 ints, these slice expressions equivalent to like that. So S is a slice with 1, 2, 3, 4, 5, 6 in there. Then S is going to be 3 and 7. So it's going to be 3 and 7. We put this in comments here to make sense. So it's going to be, I think it's going to be 3, 7. And then this is going to be S2. So then this is going to be, this is the reference. This is going to be 7. And then 0 to 2. Actually, hold on, that's not right. So 0 to 2. So that's going to be 3 to 7 again, because it's going to take from the beginning to the last. And then this one is going to be from 1 to 3. I think it's going to be 3 and 7 again. That's mistaken. Oh, whoops, I made a mistake. No, I was thinking it was the way it was done before with the comma. So like that way, it's that. You can't do that. Go back to the... Oh. One to 4, so it wasn't right. It's 3 to 5, and then that'd be 0 to 2. So, but not inclusive of the last one. So we get rid of 7. So it'd be 3 and 5. Yeah, okay. And then it would just be 1 to the end, S. 1 to the end. Yeah. So 5. Okay. It just points to that one. Right, okay. Ooh, hope people don't write call letters. Oh, videos. Thanks, Elliot. Thank you. Glad you enjoyed them so far. Let me know in the comments if there's anything, any sort of topics you think you'd want to see like videos on. Yeah, I've got some more. I've got another one come out tomorrow night. Stay tuned for that. Hope you're enjoying the ride for Golang so far. Slice length and capacity. Slice has both a length and a capacity. The length of a slice is the number of elements it contains. The capacity of a slice is the number of elements in the underlying array, counting from the first element in a slice. Let's see. Slice both length and capacity. The length of a slice, the elements it contains, the capacity of the length of the slice is. Capacity of a slice is the number of elements in the underlying array, counting from the first element in the slice. The length and capacity of a slice S can be obtained using expressions len and cap. You can extend slices length by reslicing it, provided it has sufficient capacity. Try changing one of the slice operations in the example program to extend it beyond its capacity and see what happens. So this slice, got the prime numbers, 6 of them, and a slice the slice of slice and cake. Okay. Slice the slice to give it 0 length. So it starts from 0, ends at 0. Print slice, that's 0. So extend its length so S becomes 0 to 4. So then it's just going to be a bunch of zeros, so 4 zeros. Then drop its first 2 values. So it's just going to be 2 zeros. Is that right? Huh? Print slice S. Extend its length. Okay, so when we do this, we don't actually override. Okay, so its capacity is still 6. Oops. Print slices. All right, okay, it's just a function for length is the, don't know what you called that. %d. %d, that's the same too. Oh, right. Oh, placeholders there. So that's that. That. Not sure what that means. Does that mean it's a function or something? Not too sure. And then that's the value. So the value of that. That's the definition of that. I'm not sure. Right. So even though we reduced its length, the capacity of of S was still the same. So extend its length from 0 to 4. So 1, 2, 3, 4. So it didn't actually delete stuff that was in the slice. It was still there, kind of hiding. That's interesting. But it didn't change its capacity here until we started with that. So it took 2 in, so it got rid of that. 1, 2, started there. It's inclusive. And it went to the end because we already decided that its length, max length, well, the length of the array was going to be up to 4. So it just did like those 2. Okay, a little bit weird. A little bit strange how that reduces capacity but not the other way around, like reducing the end doesn't reduce the capacity. Okay, you can extend on its slice by reslicing it. Right, so try one. Change one of the slice operation example to extend it beyond its capacity and see what it seems. So if we change that to like 8, is that gonna blow up? Slice bounds out of range with capacity of 6. Okay, yeah, that makes sense. Okay. Interesting stuff. Interesting indeed. Nil slices. The zero value of a slice is nil. A nil slice has a length and a capacity of 0 and has no underlying array. Value of it. The zero value of slice is nil, right? That's a nil slice. Even though it's got int as the type. A nil slice has a length and capacity 0 and has no underlying array. Okay. Creating a slice with make. Slices can be created with the built-in make function. This is how you create dynamically sized arrays. The make function allocates a zeroed array and returns a slice that refers to that array. The make function allocates a zeroed array and returns a slice that refers to that array. Okay, so make an array of integers with a length of 5 and specify capacity, pass a third argument to make. So give it an array of integers again, give it a length of 0 but a capacity of 5. So so take it from 0 to the capacity of b, which would be 5. So the length will be 5 now, and the capacity will be 5 now. And if you do b, 1 to the end, it'll be 4 because it skips over 1. So this function make. So it makes an array. No, it makes a slice. Makes a slice of an array of integers with a length of 5 and a capacity of 5 by inherently. Yeah. Print slice. Yep. Capacity. S. And then B is make, so same thing, but it's going to be a length of 0 but a capacity of 5. Yep. And then C is going to be 0 to 2, so 0 to 2 of that, so 2 zeros with a capacity of 5, so that didn't change. And that'll be 2 to 5, so that'll be 3 zeros. Because it's not inclusive. But it's got a capacity of 3 because we've provided both. Okay. Slices of slices. My God. What's going on with this? There's my marbles. There are 5 people really watching on Twitter. Well, it's just total views, so people might have just left. Okay. Slices can contain any type, including other slices. Okay, so create a tic-tac-toe board. Oh, that's going to boggle my mind. So it's an array. It's a slice. Go arrays. Let me find the thing again. Right, it's only an array if you start with that. And you have to give it the length. Right, okay. Remember now. So a slice. It's going to be a slice. A slice of slices. Okay. A string So it's a struct as well. It doesn't have the keyword struct. And then it's going to be 3 things along, so we get a 9 by 9 basically. So the players take turns. So 0, 0, x, 2, 2. So that'd be in the middle. 0. And then 1, 2. So 1, 2. X there. X, X, 0. And then 1, 1, 0. Where? Lost me now. Let's just print it. Zero, 0. 2, 2. Yeah, okay. That's the bottom right. 1, 2. So oh, you've lost me now. 1, 2. Okay. Oh, it's down first then, right. 2. And then 1, 0. So 1. And then 0, 2. 2 across. Right, okay. Oh, crazy. Try and juggle that in your mind. It is common to append new elements to a slice, and so Go provides a built-in append function. The documentation of the built-in package describes append. So function append. Slice with type of T versus T's, which has a slice of T. First parameter S of append is a slice of type T, and the rest are T values to append to the slice. So it can only be the same type, it can't be different. The resulting value of append is a slice containing all the elements of the original slice plus the provided values. In the backing array of S is too small to fit all the given values. A bigger array will be allocated. Too small to fit all the given values. A bigger array will be allocated. The return slice will point to the newly allocated array, so it creates a new one. Okay. So here, that's going to be 0. So this is going to be, oops. You get used to working on Windows keyboard. So appends works on nil slices. So we append another 0, right? So it's going to be like and the slice grows as needed, so it's going to be we can add more than one element at a time. So then S is going to be all that again. 2, 3, 4. Is that right? Oh, it's nil. Right, okay, so it starts off with nil, so there's none of that. Okay, nil. So there's no value in that one to start with. The range form with the for loop iterates over a slice or map. When ranging over a slice, 2 values are returned for each iteration. The first is the index, and the second is a copy of the element in that index. I always need to read it twice. The range form of the for loop iterates over a slice or map. when ranging over a slice, two values are returned for each iteration. The first is the index and the second is a copy of the element in that index. Okay? So V becomes the range, so it'll be, so say for this, going over pow, the power, so like, 1, 2, so then it'll be 2 asterisk D. So it's going to be I, which is going to be 0. V. Oh no, so it's going to be 2 asterisk 0 equals V. Oh no, sorry, I got this wrong. Right, okay, pow. Right, so it's going to loop over that, and it's going to give us, that's going to be 0, and that's going to be 1. So 2 asterisk 1 equals 0. And then 2, that'll be 1, 2. Let's see what this does. Yeah, that's what I thought. So 2 asterisk 0 equals 1, yeah. And then V in the second loop is going to be 2. And V in the second loop is going to be 4. 4. And V in the fourth is going to be 8, yeah, and so on, so on, so on. Index. That's the D is that percentage D is that, and then that percentage D is that. Okay. So the range form for loop iterates over a slice or a map. That's interesting. So that's specific to the for loop. Okay. Range continued. You can skip the index or value by assigning to underscore. For I, underscore is just unused variable then. Okay, I underscore equals range pow, or for 4 underscore comma value equals range pow. If you only want the index, you can omit the second variable, so I. Okay. So that's just I, and that's just the value. Looping over the a lot of ways to do it. It's like some really interesting, like really powerful mathematics of like formulas and stuff in this. Like I don't understand what uint means. Probably have to go back to some data science, computer science to understand that properly. It means like the first thing in this array, so it's going to be an array with 10 entries, but they're all going to be 0. So that's just going to basically set the first one in the array. It's going to be 1. To the power of 1. And it's going to be 1 to the power of 2. 1 to the power of 3. I'm not going to lie, that is like baffling me and stuff. So we will come back to that another time. I'm not going to understand that right now. So exercise slices. Implement pick. Okay. Well, this is taking me through the ring. How far down are we? Okay, not too bad. We are going through, I tell you. We're going through and we've got about 46 minutes left. Crikey. Implement pick, it should return a slice of length dy, each element of which is a slice of dx, 8-bit unsigned integers. When you run the program, it will display your picture, interpreting the integers as grayscale, while blue scale values. The choice of image is up to you. Interesting functions include and x, current y. You need to use a loop to allocate each unit array u in a instead of use u in value to convert between types. Oh boy. Return a slice of length dy. Each element. What's it do in a minute? Pick. Pick.show. What is this? It should return. I wonder if there's answers for these. It should return a slice of length dy. Each element of which pick. Each element of which is a slice of dx, 8-bit unsigned integers. When you run the program, it will display your picture, interpreting integers as grayscale or blue scale. Choice up to you. Interesting functions include x, y divided by 2, x, Let's keep it simple with that. Okay, so we use the make, is it? So UI length equals it should return a slice. So it's like int, and then what's the length of dy? What's that do? I got no idea with this one. Rather my brains on this one. Implement pick, it should return a slice of length dy, each element of which is a slice of dx 8-bit unsigned integers. dx 8-bit. Oops. Oh no. What's wrong with that? I'm not going to cave into this one. I'm going to try and figure it out. Which is a slice of dx. I'm gonna look this up. I ain't afraid. I was on the right lines a little bit. Oh, duh. Yeah, of course I don't need to do that because it's dy. Everyone's gonna see that. I ain't afraid. I'm just trying to get through this because like these examples are kind of below my little mind a little bit, so I can't quite follow them. So ret is equal to make. So we make the slice where it's going to be a slice of slices where u in a. I'm gonna have to look up some of these. I really don't understand what that typing stuff. So it's going to be go u in a. So it's an int with a length of 8-bit integers. Yeah, is a set of all unassigned 8-bit integers. Variable var, one assignment, space. Can't run it, balls. Oh no. Anything too high. So then, starting from 0 for however long dy is. What on earth is this package? What is this? Okay, so there's an array of arrays of uint8, so 8-bit unsigned integers. For dy, so length of that's going to be how long is that going to be? 0? Oh. I'm getting used to this, so it's going to be dy. See if I can remember the syntax. I think it's going to be like this. Parentheses, like that, and in double quotes, it's going to be empty. dy 256. Oops. Short command. I don't do that. 256. I don't quite follow that. Crazy. I sort of follow, but I don't understand where dy comes from. I don't really quite understand that. I'm gonna have to get into some examples to understand that. Okay, right, we move on to maps. Just about over half an hour left. Maps. A map maps keys to values. The 0 value of a map is nil. A nil map has no keys, nor can keys be added. The make function returns a map of a given type initialized and ready to use. So type vertex is a struct. It's got lat, long, and they're both flow 64s. Var m map string vertex. So make. So m is going to be make, so that's the array making function. So map word. Map maps keys to values. Map make at that point just empty map. Is that strictly necessary? Nil map. This is all just the type. That was in. Does that matter? The make function returns a map of the given type, initialized and ready to use. Okay. I'm not sure I quite understand this part. Like string, I understand that it's an empty array, nil empty array. A nil map. Should I follow that? Map literals. So map literals are like struct literals, but the keys are required. Map literals are like struct literals, but the keys are required. I'll go back to maps. I'm not sure quite. This is like the beginning maps. That's not good. That's not good if I don't understand it from the off. Let me see this. That's 7. Oh, yeah. Okay, right. Right, okay, I think I understand. So this is saying we're going to create a map. This is all the type part. Right, okay, hold on. I got my things mixed up and stuff. Right, so that's all type. That's just all type, just empty type. So then when we do make, that returns a nil version of that. Which is that. It's the same, it's still nil. It doesn't matter. But it's initialized. Hold on. Make map. Let's see this one. Make key type value type. Okay. Map types are reference types like pointers or slices, and so the value of m above is nil. Yeah, I got that part, yeah. It doesn't point to an initialized map. A nil map behaves like an empty map when reading, but attempts to write to a nil map will cause a runtime panic. Don't do that. To initialize a map, use the built-in make function. Okay. Some beeping. Just check on, is everything still good? Check YouTube briefly. Yeah, we're still live. Cool. Okay. Just checking that. Right. Okay. So it makes a bit more sense now. Right. So it's not. That's a nil. That creates a nil map, but it's not initialized until that. So it's read. It prints out there because it's read access there at the minute, but then it's not actually there. It's not filled. Okay. Map literals. Map literals are like struct literals, but the keys are required. So this is the struct lat long, they're both float 64s. So map where the key is a string and vertex is the value type. Okay. So that's without the make part. That's just like literal. Okay. Okay. Map literals continues. If the top level type is just a type name, you can omit it from the elements of the literal. If the what's the difference between that and that? Alright, okay. If the top level type is just a type name, you can omit it from the elements of the literal. Oops, wrong way. Okay, just a bit more succinct. Same thing. Mutating maps. Insert or update an element in map M. So M, the key is element. Retrieve an element. Element is M key. Yep. Okay. Delete an element. The map and the key. Test that a key is present in a two-value assignment. Element and OK equals M key. If key is in M, OK is true. If key is not OK, if not OK is false. If key is not in the map, then element is the 0 value for the map's element type. Key is not in the map, then element. Key is not in the map. The element is the 0 value of the map's element type. Zero. Okay. Note if element or OK have not yet been declared, you could use a short declaration form. Okay. Is 42. Is 48. That's going to be 0. So let's try this down. So it's going to be 42, 48. This is going to be 0. Answer, because it's going to be the We're going to delete that. We're going to try and access it. There's going to be two things, isn't it? Actually, hold on. It's going to be element and then true like that. True like that. False like that. And then v, okay. This is going to be maybe something like this. So, whoops. So the value v answer. So 0 present is going to be false. That's what I think anyway. Oh, it doesn't print that out if it's not assigned. Okay, it's just the value. Right, okay. So I was pretty much right apart from that. I don't know why I got confused with that. If you sign that, so with shorthand assignment becomes that. So v, okay. Value 0, present is false. Okay, at least I got that. Ooh. 20 minutes. How are we doing? Get through all this section, that'd be kind of cool. Exercise maps, function values, boom, forget to congratulations, that'd be really cool at the end of the day. Implement word count. It should return a map of the counts of each word in the string S. The wc.test function runs a test suite against the provided function and prints success or failure. Implement word count. It should return a map of the counts of each word in the string S. The wc.test function returns a test suite against the provided function and prints success or failure. You might find strings.fields helpful. So what does this do at the minute? Fail. So wc.test word count. So fail. Whoops. Hold on, that's that. What's this? String.fields. Field splits the string S around each instance of one or more consecutive whitespace characters defined by Unicode ISpace. Return a slice of substrings of S or an array or an empty slice if S contains only whitespace. So why is it fail? It didn't really explain. Like, hold on. Okay. So it calls the word count. Should return a map of the counts of each word in the string S. The test suite against the provided function and print success or failure. Oh. Bring that fields. I'm learning Go. So map string. It should return a map of the counts of each word in the string. Map of the counts of each word in the string. Oh. We're going to make a map there. So word count map is that slice of words. So then we do for what is it, range for go range for I've forgotten already. So the index and the value range in slice of words. So then we for this, so we do word count map, and then this and be the value equals, so we do plus equals 1, plus equals minutes. Right, why does that give me strict. Yeah, so not quite it. We have to somehow capture the number of times the word appears. How do you do that? I have to track. So at this point, we have each word in a slice. In an array slice. And then we have a map. So as we loop through, we're going to keep a track of how many times the word shows up. There's somebody else done this one. So I did that. So a slice of words, the number, get the length of the how many there are, then make a map, rect, what on earth? So less than the length of the string. So like for this one, it's going to be I am learning Go. So 4. So 4. And then that's going to be a map of, it's just going to be an empty map. So then the first map, and then so the 0 entry in array. Plus plus. How does that work? So the mapping it's going to be SS. The first 0 index array and stuff is going to be I plus plus. Not come across that. Is that the same as... Oops. Like that? No. Yeah, it's the same. So what it does is, in our new map, right, I see, right. So the field in here, so it goes, I am learning Go. Right, so okay. So when it comes onto one with duplicates, which is not that one, this one's got duplicates. So when it goes, man, yeah, okay, right. I sort of get it. That was quite. These are quite tricky. Jeez, something I've done those before. I've been stuck on these forever. Just can't think of the. You see, it's all like long-winded the way that my code is like thinking at the minute and stuff. All right, I need to do a little bit better with like splitting things out like that. Okay, instead of trying to sort of bundle it too much. Okay. Whew. God, what a night. Function values. So functions are values too. They can be passed around just like other values. Function values may be used as function arguments and return values. So this takes a function. Fn is a function that has two float 64s and returns a float 64, and this compute function returns float 64 because it executes that, which returns float 64. God, could have got some easier examples. So highbot takes two arguments, x and y, 5 and 12, that are float 64 and returns float 64. So it gives a mass square root x times x plus y times y. Is that hypotenuse, I'm guessing? So, crikey. Math.pow. Okay. Function closures. Go functions may be closures. A closure is a function value that references variables from outside its body. The function may access and assign to be referenced variables. In this sense, the function is bound to the variables. Go functions may be closures. A closure is a function value that references variables from outside its body. The function may access and assign to the referenced variables. In this sense, the function is bound to the variables. Access and assign to the reference variables. In this sense, the function is bound to the variables. For example, the adder function returns a closure. Each closure is bound to its own sum variable. Adder returns a closure, yeah. Each closure is bound to its own sum variable. So that is different to that. So that's 0, but then x. So adder. Okay. Let's finish this. We're going to wrap up. Okay, let's wrap up. I think I'm pretty close to the end of this section, so just like wrap this up. Oh no! We might have to leave that one to next time. Function closes. Okay, so for example, the add function returns a closure. Add function returns a closure. Each closure is bound to its own sum variable. Negative and positive. So positive I adder. That'd be 0. 0 to that. Int. Trying to follow this. Some crazy examples. So func adder returns a function that takes an int and returns an int. The sum of that is 0. And the return function, so x is sum plus equals the function, so 0 in that case. We'll say if it was 1, 1 is 1. And again, I'm following this on my days. So it goes to 1, 1 to there. So it returns 1. Sum that at that part is now 1. So then when it passes in negative 2 times negative 1, I guess, is negative 2. So 1, no, it's still 1, sorry. So negative 2 is passed to here, but 1 is still inside. That's a bit of a mind bender. Yikes. Well, we will figure out the Fibonacci sequence next time. Next time. I'm going to bookmark this for... Hold on. We get better bookmarks. Ooh, sneak peek. Add folder. I'm going to add a folder of Go live progress. So we're going to do that. It's going to go into Go live stream progress. I'm going to leave it on this page, but I have to call it for now. Ooh, crikey. Cool. So that is it for today, my friends. I hope you have enjoyed this. I hope you have enjoyed watching me squirm through some difficult. I mean, the beginner ones aren't they and stuff, so that kind of suck. But we'll get there. I think some of those examples are quite difficult to figure out and not the type of things I'm used to, which is the whole point of this. It's going to push me, going to get better. So that's going to be it. Just thinking next week, there's going to be a lot of stuff happening next week. It's going to be a load of challenge streams I'm going to be doing, more in the realm of the things I actually understand. So that's going to be fun. So there won't be a stream on like next Thursday night, but I think there will be. We'll get back to doing Go the week after. I mean, we'll see. Might have to do some other things on that day and stuff, but we'll get like part 2 in. So like we'll carry on a tour of Go. We'll keep going through. We might smash it out in that session. Who knows? And then we move from there. Then we start looking at projects. So start small. I think we're just going to build an API. Or like I'm going to start building out my product API. Or maybe something else and stuff for the meantime. Anyway, just rambling now. Thanks for coming on. Thank you for everyone who left comments and stopped for viewing. Much appreciated. If you're coming back in the future, don't lose the time machine. See you next time.